So I will start. My name is Pedro, and I've developed this work with Anna and Jaime. The paper is called Myope Models, are face presentation attack detections model short-sighted. So in this presentation, I will go a bit into details regarding the problem. I will talk a bit about the methodology that we followed, some data sets that we tested on, and afterwards I will move to the results and discuss them. So regarding the problem, we saw here in previous presentations that presentation attack detections attacks are recurrent threats to biometric systems. However, most of these systems, what they do is they crop the face from a large image, and they remove background information from the image. And we couldn't find any study that followed a methodology to infer the impact of the background on different methods and if it was a systematic impact. There was also any study that analyzed the cues that the model trained on images with backgrounds learned to leverage. So this paper aims at exploring those and analyzing that impact. And also we want to see if the model is capable to generalize to one-scene attacks and to data from distinct data sets. Finally, we also analyze our model with the GradCam, especially the images that are from that include background, so we can see to where the model is looking at and what is being used for the prediction. So I will want to ask you all to look at these images and try to infer if they are from an attack on or a real image. So it's not a super tough task, but it's also not a super easy task. It is much easier to do it like this. So, or like this, and so on. So, because we have much more information, we as humans can leverage that information in our visual system and see, for instance, here, we can see how this mask is cropped. And here we can see some information regarding, for instance, the pin and the low resolution. And even if we are not aware of those elements, we are using them in our inference. So we followed 4 distinct approaches. We used binary classification, multitask learning, adversarial training, and some sort of dynamic frame selection. So for our binary classification, it is just a simple model, as we saw on the talk. So we basically have a mobile net backbone, and then we have a final task that relies on predicting if an image is real or an attack. We basically minimize the binary cross entropy loss function for this task, and that's it. But we also have multitask learning. And what is the multiple tasks? The first task is to just infer if the image is an attack or a real image. And the second task relies on discriminating the attack. So this task allows us to learn much more detailed cues regarding each attack and the particularities of each attack, hence putting a higher focus on the spoofing parts and spoofing features of an image. So here is an example of the architecture. The backbone is still a mobile net. And however, I would like to to reinforce that in this part that we aim at discriminating the attack, we also include the genuine output so that we don't lose focus of the main task. Also, we approached this from an adversarial perspective. So we try to, since we are adding information with the addition of the background, we aimed at using an approach that tried to create two embeddings and minimize the mutual information between them. And one will be training for the classification task here, the EU1, and the other one will be training for reconstruction. And here we add this adversarial loss that we are trying to maximize, or in this case minimize, because we made it so that it is negative. And we have here our classification loss that we want to minimize. In this classification, it can be binary classification or multitask classification. It works. We just need to apply some changes here. We give an weight to the reconstruction loss here, reconstruction term, and we increase the weight by 0.025 at the end of each epoch. So we also have a dynamic frame selection. So basically, from all the frames of a video, we aim at selecting the frame that is more relevant for our prediction, and afterwards use that frame for the prediction. And basically, we pass all the frames through the network, we analyze their likelihood and select one. For the tests, we use 3 datasets. NUA was the first one. It is a commonly used dataset, has 15 subjects, only print attacks, and somewhat significant number of images. And we also use the replay attack that has much more subjects, 50, 2 attacks, print and replay attacks, and in total 1,300 clips. Finally, we use the ROSE YouTube dataset that, besides having a lower count of subjects, it has much more attacks. And within each root attack, print, replay, or paper mask attack, they have a lot of different variations. And they were captured also on a lot of different devices and lighting conditions. So our first task was to train a binary classification model with and without adversarial training on these datasets, and to test on these datasets also. And we could see that when the background is present, we will see consistently better results on these tasks. And afterwards, we decided, okay, so let's explore a bit the other approaches on the ROSE YouTube dataset. Why the ROSE YouTube dataset? Because the ROSE YouTube dataset has a lot of distinct attacks, so it's easy to leverage this multitask learning. Also, in the previous slide, it is possible to see that the ROSE YouTube was the one with the largest error, even with the background. So we can see that there is a significant reduction on the equal error rate on all situations when we use background, but especially when we use the multitask learning. And we also saw that adding adversarial training did not improve in any sense. In some cases, it can reduce the wrongly classified bona fide, but in the majority of the cases, the equal error rate is higher when we add adversarial training. We also tried to see how the model generalizes for other datasets. So we used the model trained on the ROSE YouTube dataset and tested it on the other datasets. And we consistently saw, again, that using background leads to better results and better generalization capabilities too. And the multitask learning again model performs quite well. So we also tried to add dynamic frame selection. The results didn't improve, and so we discarded this idea for further experiments. And I would also like to note that when compared to the state of the art, the previous state of the art, we reported significantly improvements in the equal error rate, at least for this data set, although this wasn't the main goal of this article. So let's look at what the model is using for the predictions. And on the upper part of the slide, you can see three images that contain background, and the lower part images, the same images but without background. And just want to note that this image here, the lower one on the left, was misclassified. The other ones were correctly classified as attacks. And the first one, from the left to the right, is a replay attack, a paper mask attack, and a printed attack. So let's look a bit to what the model is using. And here on the replay attack, we can see that the model is focusing its attention, or not quite attention. Attention is a different meaning on deep learning systems, but it is focusing on reflections. That is a cue that we can say that humans also leverage for this type of prediction, at least to infer if we are talking about a reflection or a video in this case. And in the second image, on the printed paper, we can see that the model is capable of detecting the pin and leveraging the information of the pin to say that this is an attack. And if we go back and look at the paper mask, we can see that here the model finds all the information that it needs on the mask itself. So it doesn't go to the background at all. Okay, finally, we also explored the capability of the model in the unseen scenario. So basically, sorry, but all these values are in percentage. Forgot to add it here. And we found that the attack 4 is quite difficult when it's not present in the training set and is seen only on test set. It gets quite a low score. The attack 4 is a replay attack from a MacBook device. That is a device with a high resolution. So we believe that it makes the task much more tough than the remaining. So that's it from my side. Any questions that you have, feel free to ask. And thank you for watching.